Hello there. This video is about SimPy, Python, and generators in Python. Kind of a mix of history in this one. So suffice to say, I get involved with doing discrete event simulation from time to time, and I encountered this response to something I had posted actually, of somebody saying that they are the inventor and designer of SimPy. Honestly, pretty hard to validate that, but just it was an interesting read. And out of it, they claimed that there was a an essay, or they called it a paper, but as far as I could find, it was just like a text-based post online about some early implementations of how to do like generators in Python, because Python did not always have generators, and they came out in like the early 2000s, or like 2000, 2001, something like that, where you could use generators to create a kind of limited coroutine like behavior. And then coroutines apparently got this guy into building SimPy. So we're not going to read through his post, but of course you can read through this later since it's on the screen. What I want to read is the paper that he mentioned, just for the historical context of understanding the history behind the SimPy Python package. Okay, so it's titled Generator-Based State Machines and Coroutines by David Mertz, PhD. Not sure what Functor Gnosis Software Incorporated is. Didn't look it up. It's fine. January 2002. So as far as I understand, this is post the release of generators in Python, but not long after. So SimPy generators introduced in Python 2 may be used to simplify state machines and simulate coroutines. Now, isn't that interesting? It's an interesting choice of words to say not implementing coroutines, but to simulate coroutines. That makes me wonder what would be a formal definition of coroutine. So if you know of one, I'd actually be interested in knowing a definition, something that I could carefully reason with. Simulation in computer science usually means some kind of either isomorphism or at least homomorphism of you have your system and it can copy all of the moves and state, or at least map to them in a desired way. So, okay, let's continue on here. So a much earlier charming Python presented an abstract pattern for state machine processing. So it's true, a lot of this all just boils down to state machines at the end of the day, and how do you want to write instructions for them to get computers to do what you want to do. Since that time, the introduction of simple generators has provided some even more natural paradigms for describing machines. Okay, I could buy that. I mean, generators are a nice way of basically releasing a value when it is asked for rather than returning right away, would be a very superficial description of generators anyway. And so coroutines are an exotic flow mechanism that few widely used languages allow, not even non-stackless Python. I guess that was true back in 2002. Of course, it's become a much more popular programming mechanism. Turn that off. Among many languages that now have async await keywords, and I don't think we'll get into it here because this is too old, but in the history of coroutines, sort of the first generation of them, so to speak, was this early usage of generators. And then you could kind of do a handoff mechanism, which I think was released in Python in 2013, I think, where you could have the yield from pair of keywords together to yield from one generator to another. And then in, I think it was 2015, we got the async await keywords in Python that is what is now called native coroutines, native in the sense that they are part of the Python programming language. But yeah, anyway, let's keep going. That's just like a short version of the history. Very, very superficial, of course. But Python's new generators, however, get us almost all the way to coroutines. And the extra few steps can be faked. Nothing like faking it until you make it. All right, so don't do. Anyway, explanation of the relevant concepts are accompanied by code examples. Nice. So what is Python? Does anybody actually need an explanation of what Python is? We're going to read it. But anyway, Python is a freely available, very high-level, interpreted language developed by Guido van Rossum facts upon facts. I guess it's very high level in multiple senses. Like if you compare it to C, it has abstractions above what C has, and it has even further, being built itself, or at least the C Python interpreter is built in C. That C language was already kind of considered high level on top of assembly, and assembly already gives us some nice abstractions on top of machine code, like actual binary. So there's a lot of layers to Python, and it's got a lot of stuff that looks like magic if you're used to so-called lower level programming languages. Okay, it combines a clear syntax with powerful but optional object-oriented semantics. I mean, whether you find the syntax clear or not, I find it pretty clear. A lot of people do. Maybe not everyone does, but that's okay. I don't really like the word powerful. It's just kind of like, it's just not a very useful word. I don't know what it means. Okay, but optional. Okay. Object-oriented semantics. Yeah, I mean, a little bit of object-oriented programming is fine. I tend to side on the objects without, or like defining classes, but not using inheritance, I think is usually okay. A little bit of inheritance is also okay, but I don't personally like deep hierarchies of inheritance. And I don't usually like multiple inheritance for almost anything, really. Okay, so Python is available for, is that true? Maybe mixins are okay sometimes. Anyway, story for another time, other things to dig into. So Python is available for almost every computer platform you might find yourself working on, and has strong portability between platforms. Yeah, at least like a lot of desktops anyway. I mean, it definitely works on Mac OS, and it works on various Linux and Debian-based kind of operating systems. It works on Windows if you install it on Windows anyway. Yep, you can use it in a lot of places. I mean, there's some things that Python probably shouldn't be used for. Like, honestly, I think if you're trying to like program embedded systems that have to be very resource limited, Python is just like a disastrous idea. But you know what? It's really great for rapid development and prototyping and stuff like that. Okay, so move on to an introduction here. It takes a while to completely get Python 2.2's new generators. I'll take this is such a time-based thing of like this is historical. So generators I've been familiar with for many years, but if you were used to no generators and then suddenly generators became a thing, I could see it being something you'd have to think about, get your head around it. But there's so many tutorials and stuff. If you currently are watching this and you don't know about Python generators, there's a ton of resources to teach it. So better than ever, I guess. Okay, so even after writing an earlier charming Python installment that introduced simple generators, I could not say that I fully understood the gestalt of generators. Okay, fair enough. I mean, I've encountered new concepts in programming, new to me, and had to sometimes not just sit with it, but also try to like build stuff with it to see how it works, and then it kind of clicks how it is. This article presents some additional patterns for the use of generators and hopefully brings both myself and readers further into the mindset of resumable functions. Yeah, I mean, if I was going to give a really superficial definition of coroutines, they are functions that you can pause and then resume again to continue execution through them later. There is a lot, but I'd still love a formal definition, by the way, if anybody knows one. So anyway, there is a lot of good about simple generators, okay? In addition to offering more natural ways of expressing the flow of a class of problems, not 100% sure what that means. Maybe like a flow of data through a computation graph, maybe? I'm not sure what that means. Generators prove to make many problems dramatically more efficient. So they can, and I used to use them a lot for instead of pre-computing a whole bunch of inputs for some function or something and applying the function one at a time to each thing, generators can be nice for creating a recipe to one at a time produce the inputs to some expensive thing, or even if the calculation itself is not really expensive, but there's a lot of options to try. It can be very useful. It's actually almost like a necessity if you are searching an infinite-sized graph for graph theory problems, of going like you need something that basically only makes one candidate at a time. Generators are one way to do it. You know, you can't load an infinite structure in your computer's memory, so you usually have to create some way of making things one at a time. Okay, so in Python, function invocation is rather expensive. That's what I've heard. I haven't like timed it, or at least I don't have any recent memories of timing it, but it does cost something. Like it does add extra operations to define the functions and to call the functions. The invocation part is the calling part of just when you call it. It has to put some things together behind the scenes. Okay, so among other factors, function arguments lists take a while to sort out. Positional and default arguments need to be parsed, among other things. They do? Yeah, okay. Interesting that that's what they thought was the expensive part. I don't know enough about this, but it's interesting. Also, initializing a frame object takes some setup steps. This is what I thought was expensive. According to Tim Peters on complang.python, over 100 lines of C. Okay, but that's not like a great way exactly to say why something is expensive. Maybe very, very roughly, but yeah, I'm not sure what counts as like 100 lines. And also that depends on what style of like, the brackets you use. I actually don't know off the top of my head which style of bracketing the C Python and C language implementation uses. But anyway, like I don't think that this is a super useful measurement, but I guess it's a start. It's a start. Okay, I have not examined the Python source myself. Okay, we're in common company, at least translating across a couple decades. Yeah, okay, fine. So resuming a generator, in contrast, is quite cheap. The arguments have already been parsed. Oh, that's an interesting thing of like, yeah, it is reusing some stuff. So maybe there is some efficiency just because of that. I was thinking about just like preparing lots of inputs or things for a search space and stuff like that. But I guess, yeah, maybe. I could believe that. And the frame object is just sitting around waiting for resumption. Almost no extra initialization is needed. Interesting. Okay, so of course, if speed is tantamount, you should not be using a bytecode compiled dynamic language. Words of truth right there. If you want high performance, I just don't think that Python's the right option. There are other bad options out there if you want bad options, but yeah, there's a lot of other better options to date of languages that will just simply because they're statically typed, ahead of time compiled, and no garbage collection. There are languages you could name that are faster, including the language that the C Python interpreter is written in. Okay. So anyway, but where speed is not the primary concern, faster is better than slower. Oh, but even when speed is not the primary concern, faster is better than slower. I mean, I agree with that. I think the major kind of arguments in favor of Python have more to do with ease of writing developing the code, as well as I think it's a little bit more beginner friendly, in my opinion. Could be wrong, of like getting started with some basic scripting and stuff without needing to know as much about type systems quite as rigorously, or memory management. You don't have to know much of anything about memory management other than that when stuff becomes... If you succeed at filling and getting a memory overflow, congratulations. But, it's pretty friendly as a language, I think. Okay, revisiting state machines, which for us, since I haven't read earlier posts, articles by this person, this will be our first time seeing what they think about state machines. Although if you Google the term state machines, or you look up specifically like finite state machine, or state machines anyway, there's lots of information that'll explain them to you. Okay, so in Charming Python number 4, I presented a state machine class that allowed users to add as many state handlers as were needed for a given machine. Okay. In the model, one or more states are defined as end states. Sure. That's usually how state machines are defined. If you're not familiar, that there's going to be some terminating set of states. You get into one of those states, the computation is done. And exactly one state is defined as a start state. Calls to the class methods configure this. Okay? take their word for it. I don't know anything about their implementation. Each handler has a certain required structure. A handler would perform a series of actions, then after a while return to a loop in the state machine's run method, with a flag indicating the desired next state. Okay. As well, a cargo variable was used to allow one state to pass some unprocessed information onto the next state. Okay, interesting. Kind of makes sense. Some context. Sure, okay. I don't know exactly what they wrote for the class just from that description alone, but it gives me some rough idea. A typical use for the state machine class I presented would be to consume input in a stateful way. Sure, I mean, the whole idea with state machines is they have state and they have state transitions. For example, a text processing tool, text to HTML, reads lines from a file. Each line needs to be processed in a particular fashion, depending on which category the line belongs in. However, one often needs to look at the context provided immediately prior lines to determine which category the current line belongs in and how it should be processed. I think I got a little bit lost in that sentence. Let's try again. However, one often needs to look at the context provided by immediately prior lines to determine which category the current line belongs in and how it should be processed. I guess I'm okay with that. An implementation of this process built around the state machine class might define a handler, capital A, that reads lines for a while and processes them in an A-like manner. I'm not 100% sure what an A-like manner is. Some kind of way of saying how to handle the states of the system, I suppose. Or it's like an additional modality. Not quite sure. After a while, a condition is satisfied such that the next batch of lines should be processed by the B handler. Oh, I see. It's like, I think so anyway. This is like partitioning the program and saying that you're handling different parts of that program or input data differently. I think I'm okay with that. A passes control back to the run loop with the instruction to transition to the B state. Oh yes, A and B are states of the state machine. Good, okay. Along with any extra lines that A could not properly handle and B should before reading additional lines. Eventually, some handler passes its control to some states designated as an end state and processing halts. Okay. For the concrete code example, in the prior installment, I used a simplified application. Rather than the process lines, I processed a stream of numbers that were produced by an iterative function. Okay? I mean, this is okay background. It's not highly insightful yet about coroutines and the SimPy discrete event simulation stuff yet, except that we've touched on coroutines. And I assume that coroutines are somehow going to be explained in terms of state machines or how they make a state machine better or something like that. We'll see. So for this installment, we look at another way of implementing the same numerical stream handling using generators, okay, with some extra wrinkles and capabilities. Okay. But a more sophisticated generator is likely to deal with something more like the input streams mentioned in the prior paragraph. It is worth reminding ourselves about the earlier state machine with an abridged version of that code. Oh, nice. Okay. So I see that they're importing from what I assume is one of their own files, modules, the state machine class. And then I see the handlers here. So one's counter takes in a value. Look at this. No type annotations. You can tell this is older Python, but in case that wasn't really obvious, how about this print one's state? Oh, yes. And look at this trailing comma. So some of you may not be familiar with this, but if you wrote out, just make an example here. There we go. If I were to go into Python here and, I don't know, just put a number, and then put a comma, you can see that it would return like a none type, because implicitly with this comma, it's interpreted as there's a none here. But actually, the The print statement is truly just a statement and not an expression in Python, but the old print statement in Python 2 actually was an expression, not just a semantically meaningful statement. Interesting to see this. I don't see this in Python code today. Okay, so while 1, which 1 just being de facto a true value, is just going to loop forever, notwithstanding some kind of breakout condition. So if value is less than or equal to 0, or if value is greater than or equal to 30, new state is bound to the value of out of range. And these one-liners, that's not super great, in my opinion, as a code style, but that's okay. We're just reading some code in its historical context here. So you break out if that happens, out of range. Otherwise, if the value is between 20 and 30, you bound to the value of the new state is in 20s and break. Else, if it's in the interval of 10 to 20, not including the upper bound, then the new state is bound to the string of 10s, and again break. Otherwise, do this formatted print of the value of the float to some number of decimal places, and then bind outside of this if block, bind to value the mathematical function applied to value. Then print this, this looks kind of like a, what is this for? For showing that a state transition has happened or something like that. It's just printing some symbols anyway. Return new state and value. So this is this one's counter function. And apparently there are other handlers, but you see the math function here is defined down here and takes n. And we've got a local import. Anyway, I don't know that you would want to put an import in there. I feel like that should probably go at the top of the file, but that's whatever. So anyway, you go absolute value, calculated on the value of sine of n, where n was the input to the mathematical function, and for whatever fun reason, we multiply by 31. Then we're going to run the kind of main name of the function, where we create or initialize a state machine. We add a state ones counter handler, add another state called tens, and the tens counter, add another state, 20s, out of range. Out of range took a few more things, didn't it? I wonder, okay, so end state is 1 probably means that it is an end state, but I'm not sure what none means. Maybe there's no handler function for it is maybe what that means. I'm not familiar with the implementation of the state machine. And then run 1, I imagine means some like setting a maximum time or something. Maximum number of operations, although 1 would be a very weird number to pick. Not sure why you pass in 1. Honestly, don't know the implementation. Readers further interested in the import state machine class and how its methods work should take a look at the earlier installment. Not sure where to find it. Maybe if I took this URL and modified it, we could look for it sometime, but I'm just going to keep reading. I'm not here to read about the state machine. You can look up many implementations of state machines, and I think I get the gist anyway. Besides, we're going to see an implementation of a state machine using generators, so there you go. The entire generator-based version of our state machine is slightly longer than the code examples I prefer to present in this column. Okay. However, the below code sample is the entire application. No separate state machine module is imported for support. Okay, nice. I kind of am hoping for complete examples here. In total, this version is shorter than the class-based one. Okay. And we will see that it does something extra, very powerful. That's exciting. All right. I mean, I don't know what powerful means, but now I'm excited. So, from future, import generators. Not a thing you have to do anymore, but yep, it was a thing. Okay, so then import the system library. Okay, we've got our math function. From math, import the sine function. While true, yield n. And then n gets bound to the value of the absolute value of sine of n, then multiply by 31. So that iterative function before becomes a generator, and this function jumps targets, not state sensitive, only to simplify example. Not sure what that means. Jump targets not state sensitive. Jump to value. If, oh, we got these lovely one-liners. Return 1s, return 10s, return 20s. This all looks similar to what we saw before. Okay. Get 1s. Oh, global, and I'm guessing mutated state variable. Why not define this, like if it's going to be global anyway, maybe I'm forgetting some things about how Python and scope, like Python 2 and how scope worked, but wouldn't you want to just stick this at the top level of scope anyway, so you have access, it just exists? Why define that? Interesting. Oh. Yeah, I see. I personally, maybe it's just a style thing, but I would probably like pass this from function to function or make it composed when the state machine runs on it or something. Yeah. Anyway, okay. So while true, print one state while jump to cargo equals 1s. So there's the value jump to, and interesting that that's cargo jump to value. And so value must be a number to make those comparisons make sense. And then print the string of the number. So really cargo here is actually not like really extra data, but it's just the value here. So cargo, iter, next. This is the difference between Python 2 and Python 3. Python 3 you actually call next on the generator as a function where the generator is an argument. Where old school, it was a method of iter, a method of the generator. And then you yield, jump to cargo. Okay, you yield that tuple. Great. Now, get 20s, global cargo, while 1, print the state name, do another one of those jumps, print the float for the cargo, get the next element of the iterable, yield, jump to cargo, cargo. You can start to see the pattern here of some of these steps that are repeated every time. And then we got the exit function that takes an iter, jump, raw input. Raw input is the old Python 2 built-in function for what is now just called input in Python 3. So you could ask, coroutine jump, and I guess you take that input in, put it into upper form, jumping, print the jump, yield jump, iter next, print exiting from exit, and then you do system exit. Okay, so that's how you can basically quit out of this loop, I guess, in a manual way. It takes user input to do it. Scheduler, you take in gen DCT, generator dictionary, I guess, and start, globalize cargo, coroutine equals start. Was that a function defined up here? Did we already read that? Maybe not. Start. Oh, right. No, start's just the name of this argument. Never mind. That's where it comes from. And while 1, you unpack coroutine cargo from, this is probably a dictionary given this square bracket notation for coroutine, value of whatever start was, probably. So gen dictionary, and then you grab and iterate to the next value of the iterator. Okay, so then to take a look at how you use this code, number stream, math generator of 1. So the math generator is just going to keep making this recurrence on n. And then we do the num stream, call next. Okay, I guess this is just initialization setup. And then you create your gen dictionary. So it confirms my suspicion that gen dict is a dictionary, 1s, 10s, 20s, whatever. And this is literally a dictionary of these generators with their initial inputs, the num streams. Okay. And then we use our scheduler. So gendict jump to, called on cargo. So there are a number of observations. Do I want to say anything else about this implementation? I don't think so. It's not it's a pretty straightforward implementation that basically prints out some stuff and changes state and prints each state. There are a number of observations to make about our generator-based state machines. Good. A first point is fairly cosmetic. Okay. We arranged state gen test to use only functions, not classes generators. Okay. Okay, that's fine. To my mind, at least, have much more of a functional programming feel than object-oriented programming feel. The code does have a somewhat more functional feeling to it by passing around some state and acting on the state. It's very pure function-like in that sense, except to the extent that it's got a global variable that's consistent with functional, but it feels glaring to me to do it in this way. There's functional ways you could do this without the global, but that's fine. Okay. What else? But one could easily wrap the same general model in one or more classes if desired. Yeah, I agree. I mean, I think most things, if you could write it out one way, you can probably do it the other. Rule of thumb. The main function in our example is scheduler, which is perfectly generic while being quite a bit shorter than the state machine class in the earlier pattern. Okay. The function scheduler requires as arguments a dictionary of generator-iterator objects in instantiated generators. I see. Yeah. Okay. The string names given to each generator can be whatever one wants. The literal names of the generator factory functions is the obvious choice, but I used capital keyword names in my example. Yes, you did. The scheduler function also accepts a start state as an argument, although perhaps a default value could be selected automatically if that was desired. Sure. Each generator scheduled obeys some simple conventions. Each generator runs for a while, then yields a pair that contains the desired jump and some cargo, just as the prior model. Right. I mean, this seems so far like an accurate representation of the description of the code we went through. No generator is marked specifically as an end state. I did notice that. Instead, we allow individual generators the option of raising an error to break out of scheduler. Specifically, a generator will raise a stop iteration exception if the generator falls off the end or gets to a return statement. Okay. One could catch that exception or a different one if desired. Sure. You can always kind of go try, and inside that, whatever code might fail, accept, and then whatever exceptions you want to catch, and then handle it in whatever way. In our case, we use the system.exit to terminate the application, which is encountered within the exit generator. Yeah, I saw that. Okay, so two more small notes on the code. Instead of an iterative function to generate our numerical sequence, the above sample uses a much cleaner looping generator iterator. I don't know if it's cleaner or not, but because I, first of all, didn't see the previous example, but I'm not really sure what clean means. I think that some code is cognitively easier for me, but I've also noticed that it can differ between people on what's cognitively easy. So it is to this person. I'm willing to grant that. No problem. Whether I would find the same comparison to be true, I don't know. So rather than have continually to pass back in the last value, the generator simply issues an infinite, indefinite stream of numbers with each successive call. Right. It is a nice, albeit small, illustration of a generator, as well as the above isolates the state transition table in a separate function. Yeah, that is interesting, and I think I like that. Like the idea of having a state transition table as like a distinct piece of code to point to. In a realistic program, the state transition jumps would be much more context dependent and would probably be determined in the actual generator bodies. This approach simplifies the example. For what it is worth, we could have simplified even further by producing the generator functions out of a single generator function factory. Yeah, I noticed that. Like the generators are highly similar in this example, and so you could have abstracted to create a factory for them because they're so regular in their structure. Okay, but the general case would not have each generator so similar to the others as to make this feasible. Yeah, I totally agree with that. There's no reason to make exactly that pattern. And while I understand and mostly agree with the dry principle, don't repeat yourself, I think that sometimes it is a smart idea to leave things repeated for future divergences in how they're supposed to work. Food for thought. And this is a toy example anyway. Doesn't matter. Okay, getting into the yummy bits here. Coroutines and semi-coroutines. So that's one thing I want to understand better is like, what is a semi-coroutine? I honestly don't know what this is. Careful readers will have noticed that we have actually smuggled in a much more powerful flow control structure than was initially admitted. I guess I wasn't careful enough because I'm not sure what was snuck in. I'm just enjoying being, from the Python 3 universe. I think I wrote a teeny tiny amount of Python 2, but I'm so used to the features as they have been for a couple of decades plus now that I don't know. I guess I didn't notice. Honestly, there is more than a state machine going on in the sample code. Okay. The pattern above is, in fact, effectively a general system for coroutines. I don't know how that's more than a state machine. Like a state machine is already a highly general thing. In fact, like the entire computer that this code is run on is a state machine. So I don't know, but it is something that's maybe more in some ways actually more specific rather than more general. Of going, this is added structure rather than saying it's more general. Anyway. Most readers will probably need a little bit of background here. Yes, I know I do. I'm reading this specifically to get some kind of juicy bits of context here. So a coroutine is a collection of program functionality that allows arbitrary branching into other control contexts and arbitrary resumption of flow from the branch point. So I think a lot of things don't allow arbitrary resumption. A lot of things allow arbitrary branching. There's a lot of different ways of creating branch points and like cycles in Python where you can go round and round and round. Okay, so the subroutines, familiar in most programming languages, are extremely limited subcase of an extremely limited subcase of general coroutines. Interesting. Still don't know what a coroutine is exactly. Other than like a pausable function, right? A subroutine is only entered from a fixed point at the top and only exits once. It cannot be resumed. A subroutine, right, versus coroutine. Sub versus co. Subroutine here is basically a function. Yeah. Okay. So as a subroutine always passes flow back to its caller, right? In essence, each coroutine represents a callable continuation, although adding a new word doesn't necessarily clarify things for those who don't know it. Yeah, I'll have to admit I don't know what a callable continuation is. Let me know in the comments if you want to explain it, but we'll keep going here. An illustration in Randall Hyde's The Art of Assembly goes a long way to explaining coroutines. So, two coroutines in action. I am not sure if this link will, in fact, work. Let's try it out. Let's take a look. So we got process number 1. Oops, sorry, that in a bad place for you to read it. Process 1, process 2. So we've got coroutine process 2 goes forward. And then in terms of directionality, there's a directionality here that goes co-call process 2, I guess, gets process 2 started, and then co-call process 1 goes back to co-call process 2, and then this also co-process 1 goes forward. It looks like there's a bit of back and forth. Like, first of all, you can have cycles, co-call sequence between two processes. It's not actually like a sequence. because there's cycles in it, for one thing. Interesting. And here we've got another cycle, and then we have another cycle after that. Interesting. So see the resources for Hyde's general discussion, which is good. I might later. We'll see. Despite the negative associations, one can note that the infamous goto statement in many languages allows arbitrary branching too, albeit in a less structured context that promotes spaghetti code. So I remember using a little bit of gotos in some of my earliest programming days outside of Python, but I didn't stick with it long. Yeah, I could see that. Because like unlike a loop where you can kind of see that there's the context, you go down, and you go back to the top, and then you go down. Go-tos, you can really just hop from one piece of the code to a completely different piece of the code and go all over the place. It's very bad for what the HTMX people call locality of behavior. Interesting. So Python 2.2's generators take a big step towards coroutines. That is, generators, unlike functions or subroutines, are resumable and can yield values across multiple invocations. However, Python generators are only what Donald Knuth describes as semi-coroutines. Interesting. A generator is resumable and can branch control elsewhere, but it can only branch control back to its immediate caller. To be precise, a generator context, like any context, can itself call other generators or functions, even itself recursively, but every eventual return must pass through a linear hierarchy of return contexts. Python generators do not allow for the common coroutine usage of producers and consumers that freely resume in the middle of each other. Do I understand that? I think I only partly understand that. So if I understand it right, I mean, it's the whole idea of you've got these locally scoped calls. So a generator is resumable, that's fine, and can branch control elsewhere, but it can only branch control back to its immediate caller. So I think what they're saying here with like full coroutines is that you can branch control to anything among a set of things that we would call producers and consumers. That is a more general network topology than just whatever network topology is made by the call or called and caller relationship. Still seems pretty general to have semi-coroutines though. This is interesting. Okay. Luckily, full-fledged coroutines are quite easy to simulate with Python generators. The simple trick is a schedule function exactly like that in the above sample code. I didn't even notice that we had simulated that. To me, it just seemed kind of natural and obvious to have a scheduler function. Okay, in fact, the state machine presented is itself a much more general coroutine framework pattern. Adapting to this pattern overcomes the minor limitations still present in Python generators and gives incautious programmers the full power of spaghetti code. Good. Just what we need. So that's very interesting. Okay, I think I did get like one little insight out of that, of at least by impression, getting a better sense of what a semi-coroutine is versus a coroutine. Good. So, state gen in action. Just them running this code, I guess, to see exactly what is going on in state gen test.py. The easiest thing to do is run it. So we go from the 1 state at time or index value 1.0, not index, but whatever the cargo value, I think it was. 20 state, 1 state, 20s, 10s, 1s, 10s, 20s, 10s, 20s. I guess I should be paying attention to these numbers, but I don't feel like going back in the code to see what ampersand versus octothorpe or hash or whatever and asterisk mean, but I'll believe for now that this makes sense. So coroutine for jump, 20s jumping into the middle of the 20s. Oh, right, this is the the raw input part that you could put in. Got it. And eventually exiting from exit. Okay. This output is basically identical to that from the earlier state machine test.py. Each line is the results represent each line of the results represents flow spent in one particular state handler or generator. Yeah, we could kind of see that from the code. The flow context is announced at the beginning of the line. However, rather than simply a call handler function again, the generator version resumes execution within a loop whenever another coroutine branches into it. Interesting. So given that the bodies of all the get under star coroutines are all contained in infinite loops, this difference is less evident. To see what is fundamentally different in the stategen test.py, look at what happens in the exit generator. Do I feel like going back up to there? Oops, I went too far. It didn't do what I wanted to do anyway. The exit. Exit here. Jump. System exit. Right. On the first invocation of the generator iterator, a jump target is collected from the user. Right, which is a simple case of the event-driven branching decisions a realistic application might utilize. Yeah, that's true. Take some user input that basically says, here's a desirable end state. Figure out how to get there. Go through whatever the control logic is to get there. However, when exit is invoked a second time, it is within the later flow context in the generator. An exit message is displayed, and the system.exit is called. The user in the sample interaction could have also jumped directly to out of range, which would exit without going to another handler, but it would perform a recursive jump into the same generator. All right. Conclusion. As was hinted in the introduction, I expect my coroutine version of a state machine to run significantly faster than the class with callbacks handler version presented earlier. So it's kind of interesting. I believe that could be true, but I actually have found, jumping forward to the present, that it's actually not that hard to write an event handling loop that is actually faster than SimPy's, that actually specifically works faster because it doesn't use coroutines. It does use functions, doesn't use classes. It doesn't have to use classes anyway. So I wonder what was true back then. I'm not sure what the implementation is that's being compared here, but it could be true. But I also think that these days it's possible to do faster computation without coroutines under, certain conditions, single thread, and that maybe you're just doing discrete event simulation. You can do that handoff faster than what the cooperative behavior is with coroutines. So resuming a generator iterator will be notably efficient. The particular example is so simple as to hardly be worth benchmarking. I don't know, I'd like to see a benchmark, but I welcome readers' feedback on concrete results. Okay. But any speed up the coroutine pattern I present might achieve is shadowed by the startlingly general flow control that it allows. It's pretty general. It seems actually arbitrarily general as a pattern. A number of readers in the Complang Python news group have inquired about just how general Python's new generators are. I think the availability of the desired framework makes the answer as general as one can want. I think that's true. I mean, I didn't look really carefully at this, but I think all of the ingredients to build a Turing-complete system is here. I think this is going to be a general way of doing computation. Not that you'd want to do all computations this way, but I don't think there's any lack of expressiveness in this approach. As with most things, Pythonic, it is usually a lot easier to program the things than it is to understand them. Give my pattern a try. I think you will find it useful. Cool. I mean, I wouldn't write it exactly this way these days, but like the gist of it is fine. And I can really see SimPy in that generator example with its process functions, right? As functions that you yield to the next event, a next process. Okay, resources. Earlier in this column, I presented an abstract pattern for a broad class of state machines. The installment is the touchstone from which I explicate the new concepts herein. I did actually try to check this out, and this link is deprecated. It's too bad, but it would be nice to see that implementation. My interview with Stackless Python creator Christian Tismer touched on coroutines briefly, along with other exotic, Stackless Python, I'm not sure what that is actually, along with other exotic flow structures like continuations, microthreads, and generators. The installment hints at some of the issues before Python 2.2 introduced generators. Of the most recent and closest connection is my effort to introduce iterators and simple generators during Python 2.2's alpha period. Several installments have touched on functional programming in Python. Given somewhat functional programming feel of generators, this might be worth looking at. Some introductions to coroutines. I'm actually really curious if that link works. Sadness. This is an old site. Randall's Hides, The Art of Assembly, also contains an introduction to coroutines, albeit for assembly. What a winner right there, though. Writing stuff in assembly. You know you're a winner then. Okay, about the author. There was a picture. Likes to write with Nietzsche that these words are the musings of an old philologist, but that untruth would unmask itself, perhaps his, right here gratuitously, plug, blah, blah, blah. Okay. Basically closing out. So that's interesting. What can we take away from this? So one thing that was interesting is that the distinction between semi-coroutines and coroutines is a thing, and that while coroutines have the ability to hand off and resume, that they are restricted in Python to where you can do this kind of call-caller relationship that is different from what you can generally expect from, sender and consumer as a different kind of model. So that's interesting, and that you can turn around and simulate the more general behavior anyway, which I think is one of the things that makes me hard to see it, is that it's so easy in Python to get around the distinction that I think they're getting at of that limitation, where you can create general communication structures pretty easily. So, but anyway, this is very interesting as a piece of history of Python and of the history of the SimPy discrete event simulation library. I'm glad to have read this. Thank you to, what was his name, Mertz, for writing this and having such an impact on the Python programming community. And for you watching, thanks for tuning in, and I'll catch you in the next one. Take care.